So we're kicking it off with a talk by Jamie Elder on how theory-laden are observations of black holes. So take it away, Jamie.
Better turn on that mic. Is that working? Great. It's wonderful to be here. As I've sort of been talking to some of you, although this work with Yulia Shtabochevsky sort of, in some ways, builds on the wonderful community that's been built by various summer schools that have been associated with projects, which this is kind of the culmination, so it's really nice to be back, talking about some of the work that grew out of that. My collaborator, Yulia Shtabochevsky. For those who know Yulia, this is about the only appropriate picture to share. This is him hiking in the Himalayas. Today, the plan of attack is I'm going to talk a little bit about recent observations of black holes, do a bit of framing in terms of some work by Melissa Jacquard on amplifying simulations and broader discussions of theory-ladenness. I'll look at some case studies and sort of sub-case studies within the LIGO-Virgo-CAGRA collaborations and the Event Horizon Telescope collaboration. And then, if we have time, tie it in a little bit to theory testing with black holes, and then have some discussion on sort of the extent to which the different ways in which these observations are theory-ladenness are or aren't concerning, or do not lead to kind of vicious circularities. Okay, so first up, we're living in somewhat of a golden age for observations of black holes, starting with observations of so-called S stars circling the galactic center, the detections of gravitational waves, which tell us about binary black hole mergers and other compact binary mergers. The Event Horizon Telescope has taken pictures of two different black hole candidates, one in M87, one in the center of our own galaxy, Sagittarius A star. And, work is ongoing. This is a picture of, from a meeting of the next generation Event Horizon Telescope project. So these are some of the people who are looking to expand the Event Horizon Telescope network in order to take more better resolution images and even videos of black holes in the future. And, for the purposes of this audience, why care about these observations? One reason is that extending our empirical grasp on black holes seems to hold some promise for tests of gravity. We've already seen some tests, and there's hope for more in the future. Potentially, if we find something weird and interesting going on, it could, if we're lucky, provide some kind of guide to help us with thinking about the successor theory. But, as we've already seen a little bit during this conference, getting empirical constraints from observations in astrophysics is really hard. We already saw this in Katie's talk and in Abigail's talk a little bit. And so what I'm going to do today is really get into the kind of the nitty-gritty of observations of black holes and get into the kind of mess of how we would actually go about trying to place constraints on black hole spacetimes. Okay, time for a little bit of framing. So, first of all, in astrophysics, I think it's clear to people here that simulations are often very much intertwined with the observations. This is partly due to the kind of epistemic situation of astrophysics. So there's a lack of controlled interventions on the target systems of interest. And one other aspect of this is long dynamical timescales. So simulations are really useful for being able to get at how systems change over time, because they change too slowly for us actually to see. So Melissa Jacquard, who I'm sure almost everyone in this room knows, has described in a wonderful paper a number of different roles that simulations play in observations. The one I'm going to be focusing on today is the amplifying role of simulations. So she says, amplifying observations occurs when the output of a simulation provides a new and sometimes unexpected context in which to interpret the data presented in the observation. The simulations provide a means by which to learn about features of the target system that they did not know about before, thus enhancing the information derivable from the observations. So there's this sense that using simulations allows you to get more out of the observations. It gives you new context that allows you to sort of see things that you weren't able to see before and learn things you wouldn't have been able to otherwise. The example that she talks about most is this case of collisions, and so she says it's through simulations that astrophysicists determined that the spokes are short-lived structures in ring galaxies, so you can kind of see the spokes in the ring galaxies there. What this tells us is that from simulations we learn that these spokes are very short-lived. So if you see spokes, it tells you something about the relevant timescales, how long ago the collision happened. So this is an example where simulations provide this kind of novel context from which we can see something from observations that we wouldn't have had any reason to notice or understand what it told us before. Now, part of what's in that example, part of what makes the amplifying role of simulations important is dynamical timescales. And black hole observations, actually, many of the dynamical timescales are actually quite short. So in the LIGO-Virgo-Kagra case, in gravitational wave astrophysics, mergers that are observed, there's change on the order of anywhere from milliseconds to minutes. With the Event Horizon Telescope, observations of supermassive black holes, the relevant timescales are, depending on the black hole and depending on kind of what timescale you're interested in, somewhere of the order from minutes to days. So these are timescales in which we really can observe. And so the kind of impetus for amplifying observations with simulations is going to be a bit different, both sort of theoretical and empirical considerations. I've just got some examples here. So in the case of LIGO-Virgo-Kagra, gravitational wave astrophysics, it's the fact that we don't have exact solutions to merging black holes that makes simulations necessary for having a sense of the dynamics of those systems and for, in turn, being able to interpret gravitational wave signals. In the EHT case, radio astronomy, you need some kind of additional input in order to interpret the pictures that they create as having sort of physical significance. In order to sort of connect that to black holes, you need to use simulations, GRMHD simulations, in order to go from sort of a picture on the sky to understanding it as a real physical system. Now, with this kind of amplifying role of simulations, because you're including many theoretical assumptions, there's of course a kind of concern about theory-ladenness that pops up. Now, Yulish and I sort of want to emphasize, we don't take theory-ladenness to be automatically a problem. It's a fairly generic feature of observation and not necessarily a bug. But in certain instances, it does seem to be problematic, namely cases where the theoretical assumptions behind the experiment bias the results in various ways, and in extreme cases make it such that you are unable to make observations that are inconsistent with the theory that you may be actually trying to test. And important for the case of astrophysics, when there's no independent check on the observations, it can make it difficult to establish the reliability and therefore work out whether the theory-ladenness is actually leading you astray or not. So in particularly problematic cases, theory-ladenness can lead to a certain kind of vicious circularity where your observations depend on theory, your theory testing is depending on those same observations, and it's really hard to get out of that circle. Okay, moving on to some case studies. So I'm going to be looking both at gravitational wave astrophysics and then moving on to EHT observations of black holes, but looking at a few specific ways in which theory and simulations enter into those observations. The theoretical background for these cases is general relativity, plus, in some cases, a bunch of other stuff. But the relevant simulations are going to be for the EHT, GRMHT simulations, so general relativistic magnetohydrodynamic simulations, always a mouthful to get out. And in the case of gravitational wave astrophysics, that's numerical relativity simulations. So here's a highly simplified schema of how LIGO works. So we start with a compact binary merger that produces gravitational waves. These travel through space and impact on the detector. It's a gravitational wave interferometer where the movement of the changes in relative length of the two arms produces a signal. This gets output as strain data, and then sophisticated data analysis procedures extract a signal from this very noisy data. So that's kind of a very simple picture of how that works. And in the top, we see the first detection of gravitational waves, GW150914. Under that, the sort of best numerical relativity simulation for those parameters, and below that, the residuals, so the noise once you subtract the signal. A slightly more sophisticated schema. What I want to emphasize is that I'm going to be talking about two features of the process. The first one is especially model-based searches for gravitational waves, the process by which you can most efficiently extract a signal from the noise. And then once you have that signal, parameter estimation. So this is where you take a gravitational wave signal, infer the parameters of the source system that produced it, and in a sense are observing the black hole itself, the black holes themselves. I'm not going to go through this in too much detail, but essentially the overall measured strain amplitude is a combination of signal and noise, and these are uncorrelated, which means that you can use match filtering in order to separate them out. This is just a signal processing technique where you correlations between a known signal and the actual data. The key thing to note about this is to use match filtering, you need to know the signal you're looking for in advance. Now, of course, we don't actually know which black holes are going to be merging at any given time, and so we don't know which exact signal is going to be going through the detector. So in practice, you need to search for a whole library of templates representing the sort of range of signals that you expect are sort of plausible. It's worth noting that while the modeled searches are the most efficient ways of extracting a signal, they're not the only way, and more unmodeled or minimally modeled searches simply look for coincident excess power in at least two detectors. And so this is, while the model-based searches are obviously very clearly theory-laden, the unmodeled searches are much less so. And so the observation of gravitational waves is theory-laden, but it's kind of mitigated by the fact that you can detect these signals otherwise. Parameter estimation is done in a Bayesian framework. This is where you take that gravitational wave signal that you found and figure out what system produced it. There's a number of physical parameters that are of interest, ranging from the intrinsic parameters describing the system, mass, spin, etc., and the extrinsic parameters, so essentially where in the sky the merger is, the kind of orientation of it relative to the observer. And LIGO, Virgo, Calgrad do this Bayesian analysis to try and figure out what all those parameters are. The key point I want to make here is that in order to do that, you need a model that maps source parameters to gravitational wave signals. And so with a given model that does that mapping, you can then go backwards using this Bayesian inference package, and it'll give you estimates for the most likely parameters to produce those gravitational wave signals. But this is entirely dependent on the model you use. And if you change the model, you change the predicted parameters of the source system. Okay, so that was a brief look at LIGO. Now let's look at the Event Horizon Telescope. This is where we get into see if my videos are working. Okay, so GRMHD simulations tell us that accretion around a black hole looks something like this. There's this sort of stable ring feature, as well as this more sort of changeable diffuse radiation, which is called the direct image. The stable ring feature we think is called the photon ring. It's actually a sort of nested series of subrings. Okay. Of course, the actual pictures that we see don't look anything like that. They're much blurrier. You can't sort of pick out the different structures that are there quite so easily as you can in this video. Now, how the Event Horizon Telescope works is they use very long baseline interferometry, which involves telescopes right around the globe. Each pair of telescopes is called a baseline, and that gives you sort of one data point on the UV plane, which is this image over on the right here. Now, that's kind of one bit of sort of one part of the plane. So if that plane was very densely filled, it would tell us that would be a whole lot of information about what the source system looks like. If it's very sparse, it means we're missing a lot of information. So, it's important to fill that plane as much as you can. And fortunately, because the Earth rotates, you end up, the telescopes sort of move relative to each other. And so instead of just being a single point, you end up sweeping out a curve in the UV plane, which sort of fills it in a little bit more. Having collected data, it's then in sort of inverse Fourier transform that gets you back to the initial image. But because of the sparseness and noisiness of the data, it's a lot more complicated than that, and sort of very sophisticated imaging algorithms have to be used in order to sort of get a reliable image, like the one you see here. I want to emphasize that, though, that the imaging procedure doesn't seem to be particularly theory-laden, because although it uses, it doesn't seem to draw on features of the source system so much as it uses sort of standard astronomical imaging techniques that are really just focused on what it looks like in the sky. And so even if they do test with synthetic data in order to make sure those imaging procedures work for very different types of sort of source brightness distributions. So instead, I'm going to be talking about some kind of further inferences that you can do with the EHT data and images. So one thing that we're interested in is learning about the parameters of a black hole, the black holes we're observing. So the EHT describes 3 different ways that they go about doing this. One is fitting geometric models to the visibility data directly. That's the sort of data before doing the imaging. But those geometric models are calibrated to GRMHD models. Another one is fitting the GRMHD models directly to the visibility data. And a third is extracting image features and then fitting those to GRMHD models. Now, the important point here is that all 3 of those methods involve GRMHD simulations. So although there's 3 methods, they're not sort of meaningfully independent in terms of the theory that's going into them. And so the EHT collaboration themselves says that because of this, a degree of caution is therefore warranted. Another case here that's kind of interesting is the use of historical data sets, which were at the time considered insufficient to be able to produce an image. But once you have the 2019 image, you've sort of confirmed that there's a central brightness depression, and it's a good fit for a kind of crescent or ring model, then you can go back and sort of build in those expectations into your method in order to look at features of historical data, despite the fact that that data alone, if you were being cautious, isn't enough to sort of give you information about the source. And so building in more theory here allows for them to draw conclusions about the sort of ways in which the source seems to have been stable and the ways in which it seems to have changed over time. And so in particular, it seems that there is a sort of stable ring feature, but that there's also some kind of variation beyond that. And so especially, where the sort of peak brightness is, the hotspots seem to change over time. And so this is a way that sort of building in more theory enables you to get more out, but it's kind of licensed by the fact that you've done the more cautious thing in getting the 2019 image first. And finally, what I want to talk about, and this goes a little bit beyond the paper, so apologies to the late stage edition here, but it's a pretty video, so I kind of had to. Let's see if I can open this to full screen. So I talked a little bit before about the photon ring. This is how it's produced. So it's produced by light being lensed around the black hole, and some of it comes directly, some of it is. So that's the direct image where things are just being kind of bent a little bit. This is going to be the n=1 photon ring, where light does 1/2 turn around the black hole before coming to the observer. And then subsequent rings involve further half turns around the black hole before they reach the observer. Now each subsequent ring is going to be both less bright and narrower. It's going to be more sort of precisely lensed into that ring structure. And then you put it all together, and you get this kind of nice composite image that looks like a snapshot of GRMHD. So, why care? Oops. The photon ring is kind of exciting because it largely just depends on the geodesics around a black hole, so it offers lots of promise for testing the actual gravity around the black hole without sort of interfering factors from accretion. Now, in 2022, a group of EHT scientists used a process they call hybrid imaging, which involves image reconstruction using models in order to sort of separate out different features of the image. One of these is an unconstrained raster model, so this is the kind of blue stuff that's diffuse and it's a sort of flexible, it can capture a lot of variety. And then a thin ring model to try and capture the photon ring. So the idea was to use this as a kind of model-based search for the photon ring and try and measure the photon ring. And in the 2022 paper, they did claim to have done so. So they said we're able to isolate the n=1 photon ring. They said they had a direct detection of the bright ring, and they said that they associated the ring emission that they detected with this method with the n=1 photon ring. Unfortunately, this seems to have been a little bit getting ahead of themselves. Many of the people who were actually part of the original paper then within the same year published a subsequent paper arguing that this really wasn't a detection. So what they did is they repeated the same analysis, but what they did is they used synthetic data to sort of carefully do the same analysis with the full image, that is the direct emission plus the photon rings. Then they did it with just the n=1 onward photon rings, and then they did it having subtracted the n=1 photon rings, so just with the sort of direct image, which is not really super ring-like. And what we can talk about their results here later, but the sort of takeaway is that they concluded that the original detection claim paper, the flux that they were measuring for the photon ring was too high, which suggests that at least some of the direct image was also being picked up on with this method. So their model-based search wasn't just picking up the photon ring, but also whatever else was there. They showed that this method is susceptible to false positives in the sense that the ring model seemed to detect a ring even when the photon ring was not present in their synthetic data. And in general, their measurements of the n=1 photon ring were systematically biased towards the direct image. So overall, using this kind of ring model was not just getting the photon ring, but also getting whatever else was there. And the problem here seems to be that in contrast to the LIGO case of template-based searches, that there's a correlation between the photon ring and the direct image, which is also somewhat ring-like. And so there's this kind of systematic bias introduced by the model-based search. Okay, so I'm going to move on now to trying to kind of at least gesture at some connections between these kinds of detections and observations and ways of sort of connecting it with theory and testing gravity. So in the case of gravitational wave astrophysics, they do a lot of different kinds of things that they call tests of general relativity. We already talked a little bit about testing the relative speeds of light and speeds of gravity with GW 170817, which is the binary neutron star merger that also produced a kilonova. Even with the very first detection, they were performing tests of GR. I'm just going to briefly mention a couple that I think are sort of relevant to the aspects of LIGO I already brought up. So the first is what's called the residuals test. So I told you that when they use a template-based search, model-based search, in order to extract a gravitational wave signal, you then subtract it and have the residuals left over. So if you're worried about whether or not those models are sort of accurate or are sort of a good match for the gravitational waves that are actually in the system, then you might worry that some of the gravitational waves are going to be left behind. And so the residuals would then have some signal still in them. So one test that they do is just testing to see if the residuals are consistent with noise, comparing to other bits of data where they don't have a detection. And so what they say here is we use this estimated level of residual to band gravitational general relativistic violations, which are not degenerate with changes in the parameters of the binary. So that last caveat there is an important point. This works well for showing that you don't have residual signal in the system, but if it's the case that changing the parameters of the binary is degenerate with changing the theory that describes the dynamics of the binary, then it's possible that the same gravitational wave templates would be adequate for extracting the signal and for detecting gravitational waves, but they would be systematically biasing you when it comes to your interpretation of the source system. And so, although this could potentially hint at deviations from GR, it could also be sort of masking them in a way. Another kind of set of tests that they do are parameterized tests. So I won't talk about this too much. Lydia Patton has a great paper talking about the parameterized post-Einsteinian framework that gets sort of incorporated into these tests. And I've talked a little bit about it elsewhere. Essentially what these tests do, though, is that they take the models that are used for parameter estimation and they add some extra parameters that allow them to sort of vary the models a little bit, and then they redo parameter estimation in order to sort of look for evidence that extra sort of changes to these models would give you also good results, or that would be favored essentially deviations from GR. So this is another way that they, despite not having alternative models of systems, because of course getting just general relativistic models is super hard, despite this they can sort of be a little bit more agnostic and search for possible deviations from GR. And I talk a little bit more about theory testing in gravitational wave astrophysics in another paper in a Philosophy of Astrophysics volume that recently came out. Testing gravity with the photon ring. Now, I already said that a little bit that the geodesics defining the photon ring are only sort of negligibly affected by accretion. But the overall image does depend on accretion. So that direct image that's sort of more changeable does depend on various aspects of your models of accretion. Ooh, I need to plug in my laptop. We'll see if I can get through. Yeah, so detecting photon rings greater than the n equals 0 would in itself be a kind of striking piece of evidence for at least that it was a Kerr black hole in the center of the galaxy. And furthermore, if you can detect and measure the properties of n equals 1 and beyond, this provides some precise measurements of black hole mass and spin. And then if you can get beyond n equals 1, this can help provide some good constraints on, yeah? Oh, here, there's one here, I thought I was being really slick, like continuing to talk while I was getting out my charger, but no. Yeah, so if you can get tests beyond, if you can detect beyond n equals 1, then things start to get really interesting. You can start providing some good constraints on non-Kerr models and potentially on alternative theories of gravity. So one paper doing some of this, looking at some of the potential here is by some of my Black Hole Initiative colleagues, Prashant Kocher-Lakota and others. And one thing they talk about is how to measure the lensing Lyapunov, I don't know if I pronounced that right, exponent, because once you get so on the left we have the relative photon rings, the photon rings relative to each other according to one accretion model. On the right you have them relative to another accretion model. And if you can start to get the relative widths and distance between them, that provides you a measurement of features of the spacetime. And so starts allowing you to place further constraints on non-GR models. Okay, so I think I'm doing pretty great on time, which is a surprise. So I'm going to conclude just by talking a little bit about some kind of more philosophical upshots here. So how theory-laden are these observations of black holes, and to what extent should we be concerned about it? When it comes to the case of observations of gravitational waves, I think we can distinguish between the detection of gravitational waves versus the more parameter estimation, the astrophysical inferences we're making on the basis of them. So the detection of gravitational waves themselves, it's highly theory-laden, but in a very benign kind of way, in part because there's independent checks on the detections with more minimally modeled searches, but also because I think that confidence in gravitational wave detection doesn't strongly depend on you having accurate gravitational wave models. You know, I sort of touched on this a little bit, but even if the templates are systematically biased in the sense that the parameters associated with those models are not really the right parameters of the source system that produce the gravitational waves, they're still going to be fine for detecting gravitational waves. It's just that your further inferences are going to be biased. This is something that Eunice and Pretorius talk a little bit about in their 2009 paper, and I've talked a little bit about in various work on LIGO. When it comes to the observations of black holes via parameter estimation, that's where things get worrying. These are highly theory-laden observations. It's just you need a model in order to connect gravitational wave to source parameters, and there's no agnostic unmodeled alternative. You could vary the model, but then you're just getting sort of a distribution of possibilities of the source of how the source system is depending on your parameters, and that doesn't really help you in determining the parameters of the source system. Besides the fact that models for non-G are so far not forthcoming. If numerical relativity results in particular are inaccurate, that would bias parameter estimation. Now, we might have good reasons for thinking that numerical relativity simulations are very accurate. My sense actually is that this is the view in the community, although the kind of reasoning for confidence in these simulations, of course, can't be to do with connections with empirical stuff so much as a kind of robustness argument, because there's a wide variety of strategies being used in order to deal with these systems. But importantly, another aspect of this is just that there's no independent access to the target systems, at least when they're two black holes. We sort of get one signal and then it's gone, and we can't observe that system again by any other means. And so when we go to test general relativity using these signals, there is real potential for it to be viciously circular, simply because there is this systematic bias, and it's kind of really hard to establish whether that systematic bias is ruining things or not. When it comes to the EHT, I said I don't think that it's theory-laden when it comes to the imaging itself, or not particularly so. But where the GR dependence comes in is in parameter estimation. The circularity doesn't seem to be as vicious, in part because there are alternative means for measuring the parameters of these systems. In M87, you've got things like gas dynamics. In Sagittarius A star, you've got mass measurements from things like the S2 star, other bright tracers. And in some, the parameters can be jointly constrained in other ways, things like connecting to jet power. And to some extent, the EHT have done work to try and rule out some non-GR models based on kind of just sort of more general features of the system. So they consider, what if the black hole's got a surface and is reflecting? And a lot of that can be seen in paper 5 of the original EHT series. Finally, the hybrid imaging of the I think looks like a bit of a cautionary tale for some of the dangers of model-based measurements in the context of astrophysics. But reassuringly, it seems that the tools for realizing that it was a problem were already there by doing developing some synthetic data, testing what happens when you sort of extract or include the photon ring and how that biases things. It was very easy to establish, in some sense, that things were going wrong. And so, while this looks like a case where things work out okay. So conclusions, in these case studies, it looks like the amplifying role of simulations and other kinds of associated models, it increases the amount of information that you can extract from these astronomical observations. It also increases the theory-ladenness of these observations. Now, it seems that at least sometimes there's kind of epistemic trade-offs to be made between information extraction and avoiding kind of theory-ladenness and circularity problems. I just want to say, Peter Gallison makes a kind of similar point related to image construction of the EHT. But it seems like lots of strategies for dealing with theory-ladenness in each of these contexts are available, though in some cases it's easier than others. Observations of black holes certainly aren't theory-neutral, and they're certainly complicated, but that doesn't in itself mean that there's a vicious circularity. You have to look at the details. And overall, I think that understanding the kind of amplifying role that simulations are playing in these different cases does help clarify the nature of our empirical access to black holes. Thanks.
Thank you very much. And for our commentary, we turn to Western Zone, Yichen Liu.
Thanks, Jamie, for the wonderful talk. I really appreciate the work in the sense like you jump into the jungle of various technical details and then you bring back a systematic and very clear philosophical work. And I do have a better understanding after listening to your work. So I have two comments and one like possible window for further discussions. And the first comment is about the theory-ladenness. But let me start with a debatable or even controversial point of view, which is that I think it's typically hard to realize the physical significant part of a theory or even the basic scope or structure of theory until we try the theory to the best, as Francesca suggested yesterday, in the sense that we need to equip the theory with various practical techniques, for example, differential equations, solving methods, and they help extend the theory and apply the theory in simulations, experiments, or interplays with other theories. Okay, so the one relevant example in this talk is the intricate relation between GR and numerical relativity and hence simulation. Because much of the simulation mentioned developed from the numerical relativity, and numerical relativity had too much building assumptions from GR, right? So how much can we say the simulations and the numerical relativity are different from GR, and then let alone the independence of the simulation relativity? And I think this point affects the discussion of theory testing and theory-ladenness in the work, because it seems not easy to specify like what theoretical claims from GR you are testing and by the observations. Like specifically, there are some points in the talk and the draft you sent me. For example, first when you talk about the LIGO-Virgo observation, and it is kind of a test of a GR, one of the tests of GR, and so, but like sometimes I feel I can understand more if the specific theoretical claims you are referring to are mentioned, right? For example, you mentioned theoretical assumptions about the dynamics of binary black hole mergers are baked into the observation, but it's not possible to make observations that are incompatible with these assumptions. So, but here still, like what assumptions or like what specific part of GR you are mentioning? Because like apart from the massaging the Einstein equation, whatever, like ADM formalism or the decomposition, but like apart from that, like, what specific assumption we are testing? Or because it's not easy to just specify it, right? And the similar case in EFT is the one I want to know more is the like because it actually is a like combination of gravitational lensing based on some theoretical models, and of course, like if you want to do theoretical lensing, you need to assume some model. It might be from GR or not GR, but like say, if the correct one you construct the data from like KL or whatever, because in the paper they say KL can be the explanation of this observation, and then like what properties of KL model itself are baked into the construction, right? Especially the ring model, like how closely the ring model is related to KL. So that's the first question. Sorry, it's a bit long, but.
Okay, so yeah, lots of great stuff here. So I'll start by, I think, endorsing what you said at the beginning about the fact that you need to build in a lot of other things in order to sort of really extract and understand the content of a theory. That's, yeah, something that I very much endorse. And I think this fact sort of builds into a kind of answer to, a very unsatisfactory answer to one of your questions, which is, you know, what specific aspects of GR are being tested here? And, you know, I think to some extent there is a kind of, you know, problem of holism that, you know, what's being tested is kind of a little bit hard to pinpoint in a lot of cases. And many of these tests are, some of them are more specific and, looking at, the arrival times of the gamma rays versus the gravitational waves in order to, really place constraints on the speed of gravity. But a lot of the other ones are more just like looking for some hint that something's going wrong, right? And, it's a little bit hard for me to say exactly what aspect of GR they're sort of would expect to be going wrong here. And in part, I think that they're kind of consistency tests that are being opened up a little bit more to try and really test whether the sort of theory-laden methods are actually masking deviations from GR. And so I think there's more work to be done in order to sort of make the connection a bit tighter between, what these tests are actually doing and what the kind of, hone in on the specific aspects of the theory that are being tested. Certainly, I think that the hope would be if there were deviations, they would be happening in the very late stage of the merger where you have strong gravity and high speeds, and we don't have simulations or models of what happens according to other theories of gravity there, at least not to the extent that we do for GR. But if things started to look different from GR, that'd be really interesting, and it might guide us towards, one theory or another. There was also a question in there about the relationship between numerical relativity and general relativity. I think I'm probably not the best person to answer that question. Although I've read a lot of the numerical relativity papers, I'm not myself the expert on these things. I think that this is one case where simulations seem to be a lot closer to what people think the theory is really telling us than in most other simulations, which are much sort of more distant from fundamental theory. I think people in this field often talk, at least loosely, about as if these were identical. That's clearly not the case, but at least there does seem to be a much tighter connection than in a lot of other simulations.
No, this is super helpful. I think we have a lot of agreements according to your answers. I like that. And my second comment is about the circularity then. You are very careful of on discussing the various kinds of circularity, and I think most of them are convincing. And there's some discussion in your paper you sent me, which you haven't mentioned in the talk, but I really want to bring to the audience. That is your reference to Woodward's discussion of Millikan's experiment, the oil drop experiment.
Mm-hmm.
And so let me directly quote what Woodward says in the paper. So Millikan's oil drop experiment, the mere fact that theoretical assumptions, namely the charge of electron is quantized, and that all electrons have the same charge, play a role in motivating his measurements, or a vocabulary for describing his results, does not by itself show his experimental design and data analysis were of such a character as to guarantee that he would obtain results supporting his theoretical assumptions. And his experiment was such that he might well have obtained results showing the charge of the electron was not quantized, or there was no single stable value for his quantity. And using this kind of reasoning, and then I want to talk about your argument that the parameter estimation in the RVC, which you think is potentially a very vicious circularity. So first of all, like the case of RVC you discussed can be divided into two stages, right? The first one is the search for gravitational wave, which is benign, and so that we can trust some kind of observational result of it. And the second one is to trace the source of the gravitational wave generation, and that one you think is a little bit problematic. So what if now, like I'm trying to apply Woodward's reasoning, what if now somebody comes to you and provide otherwise a different scheme from your understanding, and in the following sense. First, a theoretical template model is used about the binary merger dynamics to guide the design, observation, simulation, and inference, etc. And the second, inference from the template model to tell us the estimate parameter from the theoretical model that could be tested against the parameter that is observational from the first stage, as I mentioned, which is like just observational, and we can trust that. And the parameter from the observational is about the gravitational waveform, and they agree. The theoretical parameter and the observational parameter, they agree to some extent. And then third, the key step is that we have confidence in believing that the potential or hypothetical changes of some part of the theoretical model will result in a kind of less agreement or disagreement of the estimation parameters. Or we can possibly change the model to the others, even though we maybe not, like currently we don't have other models, but because of the details, we construct the model and the estimation. We know that there are some parts, if we just change it, and then the agreement will disappear, right? Even hypothetically. And then it seems like it will be a confirmation that this kind of signal detected will support the correctness of the template model. And I don't really see a circularity here by using the reasoning in the Millikan's experiment.
Okay.
Because you otherwise not get the agreement, right?
Okay, so I think I just need to clarify where the sort of independent confidence is coming in. So you described comparing to parameters from the observation.
Yeah. So according to my understanding, so the parameter estimation is done by so there are two estimations of parameter. One is based on the theoretical model, and you construct you say if there is gravitational wave generated, what would the waveform be like from the theoretical model? And then you have some estimation. And the second one is from the observation, which is corrected from the first stage of RVC, which you say that, because there's an independent, unmodeled burst search pipeline, so we can trust the gravitational waveform, for example. And then you compare these two, and it gives you some kind of confidence of the theoretical model then. And that's my understanding of parameter estimation. Maybe it's not correct, but yeah, correct me.
Yeah, so I think that in the case of the detection of gravitational waves, you do have these independent methods that provide a check on one another. In the case of parameter estimation as it pertains to the source system, what seems to be the problem is precisely that there is no such independent check. And so, because you can't get parameters about the black holes out of the gravitational waves themselves without a model, it seems like that ends up being a kind of different case from gravitational wave detection. And that in ordinary circumstances might not really be a problem. So if you were in an experimental context and you're using theory in order to get the value of a parameter, you might not be terribly concerned because you might think that there's some other ways of getting at the same parameter. There's some ways of tinkering with the system that you're working on in such a way that you can sort of establish some kind of stability of the phenomenon. You can do all the kinds of normal things that you would do in an experiment. In this particular case, it seems like most of those strategies just aren't really available. And so you have this kind of one line of evidence, and that line of evidence can only even be considered a line of evidence about a black hole in virtue of some model that you accept, that you're using to make the inference. And so we don't even really have a well worked out system of models according to alternate theories in order to make some kind of population level comparison. and see what patterns might be different on a population level. So it looks like a really hard circularity to break.
Yeah, no, I totally agree. There is no but I think Udur's the example provides me a way that even though we know there is no independent access to this observation, but we still can have a kind of argument to get rid of the vicious circularity because in the Millikan example, you really don't do a second experiment or you do the others, but you just say that even though the assumptions are building, but you can get different possible results, and why a specific kind of result happening is because it can otherwise be the other results that's wrong and doesn't support the one we in the assumption. And here the case is, we don't have other models maybe from other than GR models. And because binary merger is very difficult and sociologically people don't want to invest money into the other models. But still, we can apply the similar reasoning in saying that because in the details they construct a model and apply model to the observation, we might know the crucial parts of this connection that makes things happen. And if we slightly change it, we do know, even possibly or theoretically, the gravitational signal will disappear. The estimation of the parameter will change in a sense. So still we can say, if we are not using this theoretical model, then we will not get the correct estimation. So that it's not on purpose or eliminate the possibility of dissupporting result. I don't know if I clarify my thoughts.
Right. I think maybe I have a better sense of what you're saying.
Yeah.
Okay. So first of all, I think that I think the comparison with the Millikan case, when it comes to parameter estimation itself, it's a model-dependent observation. That by itself is not a circularity, right? Because it could just be right.
Yeah.
If we think that our models are good ones, we're just doing a model-based inference, everything looks fine.
Yeah.
The place where it starts to get worrying is if you want to also take these observations of black holes as evidence that general relativity provides a good description of these systems. Because if there are these kinds of degeneracies between changes in the kind of dynamics that's governing the system, which is to say some kind of change in the gravity theory, at least in the late stages, and some kind of change in other features of the source system. So say Eunice and Pretorius give some examples of how this could work in some modified gravity, some different gravity theories. And the concern is that in some of those cases, what you would get is that your gravitational wave templates work just fine for detection, but you're just going to be, your parameter estimation is going to, because it relies on general relativity, you're going to get results that you're going to think it's consistent with general relativity, but you're going to get the wrong parameters about the source system. So any attempt to kind of test GR through the consistency of the gravitational wave that you detected, the associated parameters with a general relativistic description, that's going to be circular because you kind of can't get out of the degeneracy problem. You can't work out whether you're seeing a system that's described by general relativity and it has the parameters that you think and everything's going fine, or alternative situation, general relativity breaks down in this context and you're just looking at a completely different system than you think you are. And so, I think that the parameter estimation itself is not circular. And the other thing to say here is that I think, I would be amiss if I didn't join everybody else in talking about closing the loop here. But there is a kind of iterative thing that's, I think, you see happening in LIGO right now. And it's a little different from closing the loop because, and it's much less strong because there are no deviations, right? There are no discrepancies that you're trying to solve. Nonetheless, you do get a kind of iterative thing where the models are increasingly getting more precise, featuring more further features, like things like different mass ratios and spins, non-aligned spins. They're incorporating more and more physical effects that can affect the waveform. And at the same time, the detector itself is getting more and more precise. It's able to get higher and higher SNR. And so there's at least some hope that this kind of iterative strategy over time is going to be doing something like what you see in either Closing the Loop or perhaps in Chang's kind of epistemic iteration kind of idea. And I think that's at least one hope for trying to solve this problem in a kind of iterative way going forward. Because of course the data sticks around and you can go and reanalyze it with new models.
Yeah, I like your thoughts, but I think we can open the discussion to everyone now.
I'm going to abuse my position as chair and jump in on this very point because, so I think I had a much cruder version of the second question that Yichen asked, which is, so just imagine that there was a kind of binary black hole interaction that wasn't something that the numerical relativists had imagined quite yet, right? So there's no waveform template, but it's something that's detectable by LIGO. So my assumption is what you'd have is a detection, but you'd have some bizarre parameter estimates because you'd be sort of fitting it to the nearest possible waveform, but it doesn't. This is the issue of systematic bias. And so the thing that this raises for me is that if we shift from thinking about LIGO as an experiment that wants to get like a 5 sigma detection to thinking of it as an observatory that's telling us about the universe by using gravitational waves, then suddenly the parameter estimation becomes a lot more important, right? And that becomes the focus. Mm-hmm. And that becomes then the question of whether you can get another way of determining the Hubble constant using using standard sirens and so on. So I'm curious now if I assume this shift has already happened, where people are now asking the question, how much control do we have over these parameter estimations? And there, I think the question of like whether your waveform templates are complete and comprehensive is maybe more pressing, or understanding the biases that would be introduced.
Yeah, absolutely. This is, almost immediately after the first, maybe not after the first detection, but after the first few, suddenly it became much more, okay, now we're an observatory, now we're trying to do astrophysics. And, there's all kinds of things about like the way that the two LIGO detectors are very much aligned. That's really good for getting a first detection and building confidence in it because you're going to get pretty much the same thing. It's really bad once you're trying to do astrophysics because you're getting the same information twice, right? And so having Virgo on the other side of the world, getting different information, it's much more important for astrophysics than it is for, getting a confident detection. And so there's kind of, now they're trying to build the network because we've got the detection, time to do all the cool astrophysics stuff, and that's, I think, where things are now. Yeah?
Just that maybe we shouldn't think about the two detectors as two separate instruments, or together with Kagra, together with all the next instruments that we will have. It's like in the case of the Horizon telescope, it's more big interferometer, and the reason why we want that is exactly that we want to have a very precise localization of the events. That is what allows them to do the multi-messenger astronomy. Mm-hmm. So, well, I don't know.
Yeah, I totally agree. Getting, having parts of the array, we'll say, with different orientations gets you better localization, it gets you some more polarization information. That itself can help in getting more precise and placing better constraints on parameters, because a lot of you get rid of some of the degeneracies that exist. And so moving forward, I think, thinking of the whole array. And
the different story will be when we will have LISA for sure.
Yeah.
Chris.
Thanks. I have an even cruder question. So the LIGO detection is a detection of gravitational waves, but to what degree, in light of all of this, can we consider this a confirmation of GR? It seems it's even if it cannot be sort of distinguished or discerned versus other gravitational theories which also predict the existence of gravitational waves. At the very least, it was the first gravitational theory which predicted the existence of gravitational waves, and as such that was surprising, and that was detected. So at the bottom, at the end of the day, how much can we consider this a confirmation of GR? And maybe, you need to, in order for that question to make sense, it needs to be said in contrast to what, or as opposed to what.
Yeah,
What do you think?
I think this is a really hard question, precisely because we just don't have well worked out models of, like, it took a lot of work to get numerical relativity to give us models of gravitational waves coming from these systems, right? And so we just don't have that kind of library of models for any other theory. And so, yes, it's consistent with GR. It might be consistent with lots of other theories. Maybe you're the kind of person who wants to put weight on some kind of novel prediction being confirmed, but if you care about unconceived alternatives or whatever else, under determination, you might just think that, this is consistent with GR, but it doesn't really help us distinguish between GR and other theories that could be producing very similar kinds of signals.
So, Luca, but just to add, this is something you mentioned in the talk, but there are a large class of modified gravity theories that predict a different speed of light and speed of gravitational propagation. And so, as Jamie mentioned, the multi-messenger rules those out. Luca.
Hi, thanks for the great talk. I was wondering, actually related to that, so in principle, as you say, it's super complicated to get predictions from modified gravity theories about this parallel merger phase. But what about the ring down phase? In that case, it should be easier to get predictions. And in principle, we could do some theory testing with quasi-normal modes, looking at overtones and stuff like that. Could you comment on that?
Yeah, I think that's exactly right, and I think a lot of the hope for being able to do better tests comes from the ring down. My sense is that LIGO at the moment isn't super sensitive to the ring down part, but that's probably changed a lot since I last paid attention. They're in the middle of a new observing run right now where they're detecting many, many, many more events because they've done lots of upgrades. So, maybe that's forthcoming soon.
I also had a kind of basic question on the second part of the talk, which is why is the photon ring important? Does that give you like a particular clear way of estimating like the mass of the black hole or some other astrophysical parameters?
Yeah, so it's very closely tied to these parameters in a way that gives you much better or more precise measurements of mass parameters, and for other kinds of ways in which it really is tied to the geodesics of the black hole spacetime. And so insofar as you can measure the photon ring, if you sort of are measuring the geodesics and the properties of the system, just the gravitational aspects of the system, largely independent from all of the messy accretion stuff. Right. And so, at the moment they're getting mass estimates essentially by sort of fitting ring models to what's there and using GR-MHD to kind of know, how much to kind of adjust where the peak ring model is to where the actual event horizon is and therefore where the mass is. But that gets a lot more precise if you actually have the photon ring as opposed to just kind of, knowledge from simulations and a kind of guess of where the photon ring should be.
And I was curious, this is also related to Yichen's first question, which is this would make it the case that you don't have to rely as much on the MHD simulations, which I assume, unlike, I take it the view of the numerical relativity calculations is more like there may be simulations, but the view might be that you're really just sort of showing how GR works in a complicated situation where you can't have an analytic solution.
Mm-hmm.
But presumably the MHD simulations are really simulations and messy and complicated. And like, so maybe if you can reduce your reliance on those, that would be a big advantage. Is that right?
Yeah, I think that's definitely right. The GR-MHD will vary a lot depending on various choices you make about how to model the accretion itself.
Yeah.
And the photon ring in contrast seems to be, it depends a little bit on the accretion, like the distribution of the accretion in various ways, but it's much, it's much less dependent on the details of accretion than other aspects.
Cool, so we have Mike, and then Nick, and then Dominic.
This is just a finger to ask more about the rings. Did I process right that we're just in an unfortunate scenario for testing GR against alternatives, and that n=1 rings are just not informative? Is it the more eccentric paths of photons that are? Is there an intuition about why?
So I think it's like that n=1, tells you something, and it could potentially, if it was, bent in certain various ways, then that might tell you something. But I think you really do need to get to n=2 to start placing real constraints. My understanding is that there's still some kinds of degeneracies between the measurements you get from n=1 and other things that could be going on in the space-time, and it's really only once you get the relationship between n=1 and n=2 that you're really directly probing the features of the space-time in a way that's not kind of going to be degenerate with something else. I'd have to. The paper that I cite here goes into this in a lot of detail, and I don't really have the details on the top of my mind, but if you're interested, we can definitely, I can point you to that paper.
Nick, and then Dominic.
So this was about
Do you want to use
what you
So this was about the non sort of viciousness of the EHT sort of verification. What I understood from what you were saying was just a sort of more complicated version of, I know the telescope works because I could look and walk over there and see it, and it's made it, it's sort of a version of that. And I just wondered then if the theory that is being assumed in doing that has any bearing on the talk that Abigail gave us, that whether these, one of the things you might get, one of the things you could get from the Hubble tension is worried about the ladder, about how those observations are going. Is there a relation between these, or are the things that they're using to verify EHT sort of just independent of those considerations? Do you know?
Well, there's certainly no distance ladder concerns because all of these things are really close. And so, one's in our own galaxy, one's, as close as you can get. And so you're really, looking at an angular thing on the sky, right? So you're still very much in the very near regime. So it wouldn't be a distance ladder concern. But, I think that, distances in astrophysics are hard in general. And so, if there's at least some, being able to translate between the angular size on the sky that you observe for the central brightness depression and the actual size of the black hole, of course, depends on having a distance measurement. So, insofar as there's uncertainty about the actual distance to Sagittarius A star, say, that would be one potential systematic error that was affecting the parameter estimation as well.
You don't have a sequence of calibrations, right?
But isn't,
That's what you have in a distance ladder.
Yeah.
And here, I just don't think.
It's just not far enough to need a distance ladder.
I see. So,
Yeah.
okay. Got it. Yeah, okay.
Dominic, and then Raymond.
Hi, thanks. Just building on Chris's, I think, first question. Chris mentioned bizarre parameters. Like, I have some naive idea of, like, we have some theory of, like, what masses we'd expect for neutron stars and for black holes, but are there sort of ranges of parameters, combinations of parameters which we could look at, which we would consider our best fit and think this is reason to be skeptical? This is reason to be think something else is going on. What would these, maybe Chris had something more specific in mind, but what would these bizarre parameters be?
So, I mean, one thing that I would think of here is there are degeneracies between like distance and inclination of the binary. So the inclination of the binary changes essentially how loud the signal is, and similarly the distance is going to change that. And so there is this degeneracy there. You can deal with that a little bit once you have a whole population, because you assume that, you know, the inclination is just kind of randomly distributed. But for an individual event, that's a big one. So actually, Lydia Patton and Justin Cabot and I are sort of working on a project where we're going back to we're doing some of redoing some of the LIGO data analysis, but we're playing around with which models are used for which observation run, in order to see what difference it makes. What if you, say, use some of the really old models that don't incorporate as many physical effects on some of the newer detections that they did the parameter estimation using the newer models. And in particular, like, we're looking at events where they have parameters that kind of stick out relative to the rest of the population. So cases like where the distance is like weak signals that they say that are at like close distance. Things like that. Looking at especially cases where there are degeneracies to see, like, how does this actually depend on which model you use. I'm sure that LIGO people could all do this data analysis much more effectively than we could, but it's, we're interested in the kind of philosophical project of really trying to understand what it takes to kind of replicate and like see difference across different models, and like what the implications of that might be for worries about systematics as a result of these models. So yeah, I think that things where there are clear degeneracies are one place that you might look within the detections, where it could be that they've said that this is a weak signal because it's coming from a distance. Maybe it's just that other parameters, it's a different inclination. Maybe it's actually bigger black holes or smaller black holes or whatever, and it's yeah.
Great, thanks, Raymond.
So I did a super open-ended comment. So I just made a connection. I wonder if this was something that you or anyone else here thought about. So the two interesting aspects of what's going on in your talk is the epistemic situation of black hole research. It's like the lack of controlled interventions and the lack of dynamical timescales, and I take those two features as something that makes simulation like uniquely applicable to research on those. And the situation in different ways reminds me of what's going on, and all the MHD talk reminded me of this, of the current status of fusion research these days. And I wondered if that was something that you had thought about or anyone else had thought about, because it seems like in that case too, the lack of controlled intervention is super apparent, and the long dynamical timescales is, well, the timescales are also difficult to probe, but that's for different reasons, for extremely short as opposed to extremely long. So I was just wondering if you thought this might be an analogous situation in some ways.
I certainly haven't thought about that specific case, but I have thought a little bit about the similarities with large-scale simulations in, astrophysics versus, say, particle physics, where a lot of those same kinds of things arise. We tend to talk about astrophysics being kind of unique because you don't have controlled interventions, but a lot of really big, complicated experiments are also such that you at least don't have the kind of control that you might like to have over the specific interactions that are taking place. Now, I think most astrophysicists would love to have the same level of control that, say, the LHC does, but nonetheless, like, some of the problems that they will cite as major problems are kind of the same in that it's, you know, we would love to be able to control which particles were interacting with each other. Instead, we have to, you know, kind of throw a whole bunch of stuff together and like be really clever about going backwards from traces and figure out what's going on. And, you know, I think that probably the fusion case is going to be something similar where, on the one hand, there's like they're very carefully controlled experiments in some ways, but really being able to make progress, you know, you would like to have this kind of control that you lack. And in that way, there is some surprising similarities, I think, between what's going on in astrophysics cases and these very sophisticated terrestrial experiments.
Well, I think we need to shift to having the discussion over coffee, and please join me in thanking Jamie. That was wonderful.